Welcome to the lecture on queuing theory. This lecture is for chapter 6 of our course Operations Research. Queues or waiting lines are parts of our daily life. We all wait in queues when we go to buy a movie ticket, to make bank deposit, to pay for our groceries in the supermarket, and even to buy our foods in the cafeteria. We are all accustomed to a considerable amount of time, waiting time in queues, but we get frustrated when the queues are too long. The amount of time we spend in queues is an important factor in the quality of our life and in broad sense the efficiency of our country's economy. It is true that we cannot eliminate completely the waiting time in queues, but certain techniques can be applied to reduce the waiting time in queues. In this chapter, we will develop some queuing models which will help us in determining how to operate a queuing system in the most effective way. The content of this chapter will be covered in 4 modules. So, let us now start our discussion on module 1 of this chapter, that is chapter 6. Let us first discuss what are the basic characteristics of a queuing system. The basic characteristics of a queuing system are as follows: input or arrival pattern, service mechanism or service pattern, queue discipline, and customers' behavior. Let us first discuss about input process or arrival pattern. Input process is usually called arrival process and the arrivals are called customers. In all models that we will discuss, we will assume that no more than one arrival can occur at any given time. If more than one arrival can occur at any given time, then we call it as bulk arrival. An example of bulk arrival may be the customers arriving at a restaurant. In general, customers arrive in a more or less random fashion. The arrival pattern can be described in terms of probabilities, and consequently the probability distribution for inter-arrival times, that is the time between two successive arrivals, need to be defined precisely. In fact, there are many arrival patterns, but in our model we will consider Poisson exponential and Erlang distributions for the arrival patterns. Service mechanism or service pattern. The service mechanism is concerned with the manner in which the customers are served. There may be one or more service facilities in the queuing system. In most situations, service time is a random variable with the same distribution for all arrivals. In queuing models, service time is usually assumed to follow exponential or Erlang probability distribution. Queue discipline. Queue discipline refers to the order or manner in which customers join lines. It describes the method used to determine the order in which customers are served. There are several queue disciplines, for example, first in, first out or FIFO, which is also called first come, first served, FCFS, last in, first out, that is LIFO, or which is also called last come, last served, LCFS, service in random order, 0, or service by priority. In, first out queue discipline, the customers are served in the order in which they join in the queue. For example, prepaid taxi queue at airports, where the taxis are engaged on a first come, first served basis. Last in, first out or last come, first served discipline. In this system, the element arrived last will have a chance of getting service first. In general, this does not happen in a system where human beings are involved, but this is quite common in inventory system. In a big godown, the units which come last are taken out first. Service in random order or 0. In this case, items are called for service in a random order irrespective of their arrival order in the system. For example, in government offices, applications for various favors are picked up randomly for processing. Service by priority. Priority disciplines are those where any arrival is chosen for service ahead of some other customers already in queue. For example, in a doctor's chamber, when the doctor is treating a patient with stomach pain, suddenly a patient with heart stroke enters. In such a situation, what the doctor will do? The doctor may ask the patient with stomach pain to wait for some time, and he can give attention to the heart patient. Here, the doctor is giving service by priority, giving priority to the heart stroke patient. Customers' behavior is another characteristics of queuing system. The customers generally behave in the following 4 ways: bulking, reneging, priorities, and jockeying. A customer may leave the queue because the queue is too long and he has no time to wait, or there is no sufficient waiting space. Such behavior is called bulking. Reneging. This occurs when a waiting customer leaves the queue due to impatience. Priorities. In some circumstances, some customers are served before others regardless of their order of arrival. These customers have priorities over others. Jockeying. Customers may jockey from one waiting line to another. This behavior is observed in the supermarket. Let me now define some other components of a queuing system. such as size of population or capacity of the service system. Size of population. The size of potential customers may be very large or moderate. For example, in a railway booking counter, the total number of potential passengers is so large that although theoretically the number of passengers is finite, it can be regarded as infinite for all purposes. Capacity of the service system. In queuing context, the capacity refers to the space available for arrivals to wait before taken to service. The space available may be limited or unlimited. When the space is limited and the length of waiting line crosses a certain limit, no further units or arrivals are permitted to enter the system till some waiting space becomes vacant. This type of system is known as system with finite capacity. Let me now define what a queuing problem is. In a queuing system, the problem is to determine the following: probability distribution of queue length, probability distribution of waiting time of customers, and busy period distribution. Probability distribution of queue length. When the probability distributions of arrival and service pattern are given, probability distribution of queue length can be determined. Probability distribution of waiting time of customers. The time spent by a customer in the queue before start of his service is called waiting time. The total time spent by him is the waiting time plus service time. Busy period distribution. Suppose that initially the server is free. When a customer arrives, he is served immediately as the server is free. And during his service, if some more customers arrive, then they are served in their turn. This process will continue until no customer is left unserved and the server becomes free again. Whenever this happens, we say that a busy period has just ended. Let us now define the states of a queuing system. There are three states of a queuing system: transient state, steady state, and explosive state. Transient state. A system is said to be in transient state when its operating characteristics are dependent on time. This happens usually at initial stages of operation of the system, where its behavior is still dependent on the initial conditions. So, when the probability distribution of arrivals, waiting time, and service time are dependent on time, the system is said to be in transient state. Steady state. A system is said to prevail steady state when its behavior becomes independent on time. Let P&T denote the probability that there are n units in the system at time t. Then the queuing system is said to be in the steady state if limit t tends to infinity, P&T equal to Pn, which is independent of time t, and this implies that limit t tends to infinity, dPnt dt equal to dPn dt equal to 0. Explosive state. In a situation where arrival rate is larger than its service rate, a steady state cannot be reached regardless of the length of the elapsed time. Here, the queue length will increase with the time, and theoretically it could reach to infinity. Such a case is called the system in explosive state. In our further discussion, all the problems and situations will be dealt with steady state only. We will now introduce some notations which will be used in developing queuing models. N we define as the number of customers or units in the system. PNT as the transient state probability that exactly n units are in the system at time t. Pn is the steady state probability of having n units in the system. Lambda n as the average number of customers arriving per unit of time when there are n units in the system. Lambda, we denote lambda by the average arrival rate when lambda n is constant for all n. Mu n is the average number of customers being served per unit of time when there are n units in the system. Mu is the average service rate when mu n is constant for all n greater than or equal to 1. S is the number of parallel service channels or service stations in the system. 1 by lambda is the inter-arrival time, that is the time interval between two successive arrivals. 1 by mu is the service time between two units or customers. Rho is the traffic intensity or utilization factor for service facility, that is the expected fraction of time the server or servers is or are busy. Capital N is the maximum number of customers allowed in the system. LS is the average number of customers in the system, where LQ is the average number of customers in the queue. WS is the average waiting time in the system, and WQ is the average waiting time in the queue. We denote PW as the probability of a customer having to wait for service. So far, we have discussed the basic characteristics of a queuing system. The characteristics such as arrival pattern, service pattern, queue discipline, and customer behavior. We have also explained what actually a queuing problem is and what are the states involved in a queuing system. We have also introduced some notations which we will use for developing queuing models. Let us now proceed to study or to develop probability of queuing process. Let us first derive the probability distribution of arrivals in case of pure birth process. The model in which only arrivals are counted and no departure takes place is called pure birth process. In order to derive the arrival distribution in queues, we make the following three axioms. Axioms number 1. The probability that exactly one arrival or birth will occur during the time interval t plus delta t is p1 delta t, which is equal to lambda delta t plus order of delta t, where lambda is the arrival rate independent of time t and order of delta t includes terms of higher order of delta t such that limit delta t tends to 0, order of delta t by delta t is equal to 0. Axiom number 2. The probability of more than one arrival during the time interval t plus delta t is negligible. This is denoted by order of delta t. Axiom number 3. The number of arrivals in non-overlapping intervals are statistically independent, that is, the process has independent increments. Now, let us suppose that P and T denote the probability of n arrivals in a time interval of length t, where n is greater than or equal to 0, is an integer. Then P n t plus delta t, which is the probability of n arrivals in a time interval of length t plus delta t, is given as follows: P n t plus delta t equal to probability of n arrivals at time t and no arrival during time delta t, plus probability of n minus 1 arrivals at time t and 1 arrival during time delta t, plus probability of n minus 2 arrivals at time t and 2 arrivals during time delta t, plus plus probability of no arrivals at time t and n arrivals during time delta t. So, now using axioms 1 and 2, we can write P n t plus delta t equal to P n t, that is the probability that when there are n customers in the system at time t into P 0 delta t, that is there is no customers in the no arrival actually during the time del t. So, P 0 t plus delta t equal to P n t into P 0 delta t plus P n minus 1 t into P 1 t plus order of delta t. Thus, the above equation can be written by simplifying P n t plus delta t minus P n t equal to minus lambda delta t into P n t plus lambda delta t P n minus 1 t plus order of delta t. Dividing both sides by delta t and then taking limit as delta t tends to 0, the above equation reduces to P n dash t equal to minus lambda P n t plus lambda into P n minus 1 t, where n is greater than 0. Now, for the case n equal to 0, we have P 0 t plus delta t equal to probability of no arrival at time t, which is P 0 t, and probability of no arrival during time delta t, which is P 0 delta t. Therefore, P 0 t plus delta t equal to P 0 t into P 0 delta t, again P 0 delta t equal to 1 minus lambda delta t minus order of delta t. Therefore, rearranging the terms and dividing both sides by delta t, taking limit as delta t tends to 0, we ultimately get P 0 dash t is equal to minus lambda P 0 t for n equal to 0. The equations 1 and 2 are known as system of differential difference equations. Now, we proceed to solve these differential difference equations. Equation 2 can be written as P 0 dash t by P 0 t equal to minus lambda, and which again can be written d dt of log P 0 t equal to lambda. Integrating both sides with respect to t, we get log P 0 t equal to minus lambda t plus a, where a is the constant of integration. And to determine the value of this constant of integration, we use the boundary conditions P n 0 equal to 1 for n equal to 0 and P n 0 equal to 0 for n greater than 0. Substituting t equal to 0, we have P 0 0 equal to 1, and then we find that a equal to 0. Thus, we get P 0 t equal to e to the power lambda t. Now, putting n equal to 1 in equation 1, we get P 1 dash t equal to minus lambda P 1 t plus lambda into P 0 t, and simplifying we get P 1 dash t plus lambda P 1 t equal to lambda into e to the power minus lambda t. This is a linear differential equation of first order, and it can be easily solved by multiplying both sides by the integrating factor e to the power lambda t, and thus integrating both sides with respect to t, we get e to the power lambda t into P 1 t is equal to lambda t plus b, where b is the constant of integration. Now, putting t equal to 0 in the above equation, we get b equal to 0. Therefore, finally, we get P 1 t is equal to lambda t e to the power minus lambda t by factorial 1. Similarly, putting n equal to 2 in equation 1 and using the above result, we get P 2 dash t plus lambda P 2 t equal to lambda into lambda t e to the power minus lambda t by factorial 1, or d dt of e to the power lambda t into P 2 t, which is equal to lambda into lambda t by factorial 1. Integrating with respect to t and using the condition P 2 0 equal to 0, we finally get P 2 t equal to lambda t whole square into e to the power minus lambda t by factorial 2. Similarly, we can obtain P 3 t as e to the power minus lambda t into lambda t whole cube divided by factorial 3. And proceeding in this way, we can find for n equal to m, P m t equal to e to the power minus lambda t into lambda t whole to the power m by factorial m. Now, for n equal to m plus 1, we have from 1 P m plus 1 dash t plus lambda P m plus 1 t equal to lambda into lambda t whole to the power m into e to the power minus lambda t whole divided by factorial m. And solving this equation, we ultimately get P m plus 1 t is equal to e to the power minus lambda t into lambda t whole to the power m plus 1 by factorial m plus 1. Hence, in general we get P n t equal to e to the power minus lambda t into lambda t whole to the power n by factorial n, which is the well known Poisson probability law with mean lambda t. Thus, if we consider the random variable defined as the number of arrivals to a system in time t, this random variable follows Poisson distribution with a mean of lambda t arrivals, that is mean arrival rate as lambda. Now, we will explain the distribution of inter-arrival time. Inter-arrival times are defined as the time intervals between two successive arrivals. Let capital T be that time and A t denote the probability density function of capital T. Then we have the following theorem. If n the number of arrivals in time t follows the Poisson's distribution, P n t equal to lambda t whole to the power n e to the power minus lambda t by factorial n, then capital T the inter-arrival time follows exponential distribution A t equal to lambda e to the power minus lambda t and vice versa. This theorem can be proved easily. For the proof, T0 be the time of an arrival initially. Since there is no arrival in the interval T0, T0 plus t and delta t is small, we may consider T0 plus t plus delta t as the instant of subsequent arrival. Instead of considering T0 plus capital T, we consider here T0 plus capital T plus delta t as the instant of subsequent arrival, as delta t is small, and then putting small t equal to capital T plus delta t and n equal to 0 in equation 4, we get P 0 capital T plus delta t equal to e to the power minus lambda t into 1 minus lambda delta t plus order of delta t. Since P 0 capital T is equal to e to the power minus lambda capital T, therefore, we can write P 0 capital T plus delta t is equal to P 0 capital T into 1 minus lambda delta t plus order of delta t. Rearranging and dividing by delta t, we get as delta t tends to 0, d P 0 t dt equal to minus lambda P 0 t. The left hand side of 5 denotes the probability density function of t, say A t. Therefore, we can write A t equal to lambda P 0 t. Now, from equation 4, we get P 0 t equal to e to the power minus lambda t. Therefore, putting this value of P 0 capital T in 6, we get A t equal to lambda e to the power minus lambda t, which is the exponential law of probability for capital T with mean 1 by lambda and variance 1 by lambda square. In a similar fashion, the converse of the theorem can be proved easily. Now, I am coming to show you an important property for inter-arrival times. The probability distribution of the remaining time until the next arrival occurs is the same regardless of how much time already has passed. That is to say, probability capital T greater than t plus delta t, given that capital T greater than delta t is equal to probability capital T greater than small t. This property is also called the Memoryless property. To prove this theorem, we consider the conditional probability formula, and then we have probability of capital T greater than t plus delta t, given that capital T greater than delta t is equal to probability of t greater than delta t and capital T greater than t plus delta t divided by probability of capital T greater than delta t, which is equal to probability of t capital T greater than t plus delta t divided by probability of capital T greater than delta t, which is nothing but e to the power minus lambda into t plus delta t divided by e to the power minus lambda into delta t, and which ultimately gives e to the power minus lambda t, which is equal to probability of capital T greater than small t. Here is an important observation. For inter-arrival times, this property describes the common situation where the time until the next arrival is completely uninfluenced by the time when the last arrival occurred. Whereas, for service times, this property is more difficult to interpret. We should not expect it to hold in a situation where the server must perform the same fixed sequences of operations for each customer, because then a long elapsed service should imply that probably little remains to be done. In this module, we have studied the basic characteristics of queuing system. The characteristics such as arrival pattern, service pattern, queue discipline and customers behavior. We have also derived the probability distribution of arrivals in case of a pure batch process, and we have seen that the arrivals follows a Poisson's distribution, whereas the inter-arrival time follows exponential distribution. We have also showed an important property of inter-arrival time, that is the Markovian property, and with this comment we end this module.